Welcome to Math with Professor V. In this video, we're going to learn about the integral test, which is a very powerful test that you can use to determine whether or not an infinite series is convergent or divergent. So here's the criteria that you need to remember anytime you're going to go and apply the integral test. If f of x is continuous, positive, and decreasing on the interval from 1 to infinity, then the sum n equals 1 to infinity of an is convergent if and only if the integral from 1 to infinity of f of x dx is convergent. Meaning, if the integral from 1 to infinity of f of x dx is convergent, then the sum n equals 1 to infinity of an is convergent. And if the integral from 1 to infinity of f of x dx is divergent, then the sum n equals 1 to infinity of an is divergent. And just to be super clear, when we refer to f of x, it's by taking a sub n and replacing all of the n's with x's and creating f of x. Okay? So basically, if you'll think back to when you first studied improper integrals where one of the limits of integration is infinity, that's one type of improper integral. You figured out whether or not they were convergent or divergent, right? You rewrote it as a limit, and then at the end you evaluated the limit. So if the improper integral converges, then the sum n equals 1 to infinity of an is convergent. And basically f of x is kind of the same thing as an. I'm just making it now a function of x instead of using a sub n. And then same thing here. If the improper integral is divergent, then the sum of an is divergent. Now, in order to apply the integral test, you have to check that these three criteria are met. First, that the function is continuous. Second, that it's positive. And third, that it's decreasing on 1 to infinity. Or basically on whatever the limits are here in your summation. So in this case, we're summing from n equals 1 to infinity, so that matches the interval. If for some reason it went 2 to infinity, then this could be 2 to infinity. Okay? And then just so you know, the value of the improper integral, if it ends up being convergent, is generally not equal to actually what the value of that infinite sum is. So one of the most common examples is looking at P series, and we can refer to that in a video I did prior. And the value of the integral is not equal to the true sum. So you'll just need to study more math to get to the point where you can see exactly how to calculate the sum, but it's not going to happen in this class. In this class, you can only find the sum if your series is geometric, telescoping, or Maclaurin. Otherwise, all we say is convergent, divergent. Anyways, enough chit chat. Let's just do some examples. So here we go. Use the integral test to determine whether the series is convergent or divergent. So here we have the sum n equals 1 to infinity of 5n over n squared plus 2. So a sub n is equal to 5n over n squared plus 2. And what I need to do is now define a function of x, and you just swap out the n's for x's, okay? So 5x over x squared plus 2. Now we have to check that the three criteria are satisfied for the integral test. So the first thing I want to check is f of x continuous on the interval from 1 to infinity. Is it? How do we answer that question? Well, think back when you were in Calc 1 and we were taught that a whole host of functions are continuous on their domain. Polynomials, rational functions, trig functions, exponential, logarithmic, etc. Pretty much everything except piecewise functions. This is a rational function. If you identify its domain, then we know precisely where it's continuous. And the domain for this function is all real numbers, right? Because the domain is dependent on whether or not the denominator could be 0, which is impossible. X squared plus 2 has no real zeros. So I could say, all right, well, the domain of f is all real numbers. So f is continuous on negative infinity to infinity, and therefore it's continuous on the subset from 1 to infinity. So that's satisfied. Perfect. Second thing I need to check is f of x positive on the interval from 1 to infinity. Well, look at the denominator, x squared plus 2, that's always positive. 5x is not always positive, but remember, I'm only interested on the interval from 1 to infinity. So that means I'm only substituting in values of x from 1 to infinity. Yep, it's going to be positive there. Not really much to do, just say yes. And then the last thing we have to check is f of x decreasing. Well, the easiest way to check in this case is to take the derivative. And what we know from when we studied increasing, decreasing functions back in Calc 1 is that if the derivative is negative, then that tells us that the function's decreasing. So here we go, derivative time. F prime of x is going to be, we need to do the quotient rule. So we have low d high minus high d low over low low. And then simplifying, this is going to be 5x squared plus 10 minus 10x squared over x squared plus 2 quantity squared. So this gives us negative 5x squared plus 10 over x squared plus 2 squared. Well, let's see. The denominator's always positive. What can I say about the numerator? Well, I want to see, is the numerator less than 0? That would mean 5x squared has to be bigger than 10. That happens if x squared is greater than 2. So it happens when x is greater than rad 2. Then it's negative if x is greater than rad 2, which is about 1.4. So that means my derivative is negative as long as we're on the interval not from 1 to infinity, but from 2 to infinity. Is that problematic? No. You can still apply the integral test. So long as the function is eventually decreasing, that's good enough for our purposes. So no panic attacks necessary. You just have to identify there's some place at which this derivative is eventually going to be negative. So then you say it's eventually decreasing. Now, do you need to go and adjust the sum and start at 2 instead? No, it's not really that big of a deal. It won't make any sort of difference as to whether or not the integral is convergent or divergent, as long as your function's continuous and you checked everything else. So I would just leave it. Don't stress too much. Okay? Very good. So then now we're going to say we can indeed use the integral test. And first, let's consider the improper integral from 1 to infinity of 5x over x squared plus 2 dx. So the absolute first thing you need to do is rewrite this as a limit. So this is the limit, pick a variable, I'll use t as t goes to infinity from 1 to t of 5x over x squared plus 2 dx. Now start thinking about how you want to integrate. Good old u sub will work in this case, right? Because the denominator is 1 degree higher than the numerator. So I'm going to let u equal x squared plus 2. Then du is 2x dx. I only have x dx, so I'll write 1/2 du is x dx. And then don't forget, we also need to change our limits of integration. So u of 1 squared plus 2, my new lower limit's 3. And then u of t is t squared plus 2. All right, so now we've got the limit. T goes to infinity. Let me take, you know, it would be so nice. Let me take this 5 out. And then remember how we have that 1/2? So I'm just going to put 5/2 outside. Integral from 3 to t squared plus 2 du over u. Wow, wow, wow. So nice and clean and not stressful. So this is limit t goes to infinity, 5/2 ln, absolute value of u. And then this gets evaluated from 3 to t squared plus 2. Perfect. So then this is going to be limit t goes to infinity, 5/2 times natural log absolute value t squared plus 2 minus natural log absolute value of 3 is just 3. All right, so here we go. As t approaches infinity, t squared plus 2 will approach infinity. And natural log of that quantity will also approach infinity. ln of 3 is just a constant. So all of this is going to infinity. And multiplying by 5/2 doesn't change that. It's still all going to go to infinity. So the final limit is positive infinity. So what does that tell me? This tells me that the integral, this improper integral, diverges. So then I know this infinite series does exactly the same thing. So that means the sum, n equals 1 to infinity, of 5n over n squared plus 2 also diverges by, and you have to say what test, the integral test. So when you finish a problem, keep in mind you need to rewrite the original series, and then you need to state whether it converges or diverges and what test you used. That, and then also rewrite it like we have it here. Okay? Now, there are other tests that maybe you would like to use instead of the integral test. For example, if you've learned about the limit comparison test, that's another nice test that we could have used on this. However, I did integral test because that's what the directions said to use the integral test, and I'm just going to exclusively use the integral test throughout this video. But keep in mind, sometimes there's definitely more than one way or more than one test that you could use to determine if a series is convergent or divergent. And a lot of the other ones are a little less involved. I would say integrating, I use it only when I absolutely have to, because sometimes it's tricky, right, to integrate. This one wasn't bad, but other times, other tests may be much easier, okay? Here we go. Let's look at another one. We have the sum, k equals 1 to infinity, k times e to the negative k. And like I said, there is going to be another test you'll learn that's easier to use than integral test, but we don't know it yet. So I'm just going to do this using the integral test per the directions. I'd say like a big chunk of doing well in math is just being obedient, you know? So follow the directions. No freestyling. F of x is x times e to the negative x. For our purposes, let me rewrite this as x over e to the x, just to make it easier to process in the brain, okay? So before we proceed, I have to check, is f continuous on the interval from 1 to infinity? Well, what's the domain of f? Does it have any restrictions? Can e to the x ever be 0? No, it cannot. So the domain is all real numbers. So then f is continuous on negative infinity to infinity. So then, of course, it's going to be continuous on the subset 1 to infinity. Done. 2, is f positive on 1 to infinity? Well, e to the x, that's always positive. And then x will be positive so long as you're on the interval from 1 to infinity. So yeah, we could just go ahead and put a check mark. The last thing I want to check is f decreasing. So again, we need to take the derivative. Here we go. Quotient rule time. Low d high minus high d low over low low. If you haven't heard the quotient rule song, you're missing out. I'll link the video where I sing it for you. Not really sing it, recite it. I won't be rude. You don't want to hear me sing. Okay, e to the x times 1 minus x over e to the x squared. And then one of these e to the x's cancels, right? So then we're left with 1 minus x over e to the x. So can I say this is always negative? Let's check. Denominator's positive. What about 1 minus x? It would need to be negative in order for the derivative to be negative, which means x would need to be greater than 1. So this is less than 0 if x is greater than 1, but not equal to 1. Oh no, is that okay? Because we have this bracket on the 1. That's fine, it's good enough. Remember how the last problem, it was decreasing after rad 2? As long as it's eventually decreasing, we're happy. It's okay. Just be specific at where it will eventually be decreasing, okay? If it's not always negative. All right, now we can go ahead and use the integral test. So then we have, let's put a consider on there for the people. Integral from 1 to infinity, x times e to the negative x dx. Very first thing, rewrite it as a limit. Limit as t approaches infinity. Integral from 1 to t, x times e to the negative x dx. Now in this case, hopefully you recognize u sub will not work. We need to use integration by parts. And when I have an improper integral, if I can do tabular, I usually do because it just makes things so much nicer. So where you would normally pick u and dv, we're going to do the tabular method, the di method. Some people put a d here and an I here. So I'm going to pick x, because that's normally what u would have been, right? And then keep taking the derivative until you get 0. And then dv would be e to the negative x dx. You don't need to put the dx. Antiderivative would be negative e to the negative x. And then one more is e to the negative x. And then you take diagonal products, always from the left column down to the right. And then the sign alternates. So I'm not going to change the sign on the first one, but I'm going to add an extra negative on the second one. If you've never seen this, I have a whole video on it. It's linked in the description. It'll change your life because look, now I'm done. Limit t goes to infinity. I already have the antiderivative, so I'm going to switch. These are going to be at the other side. And we're going to have negative x e to the negative x. That comes from taking this product. And then I need this product, which is going to be minus, don't forget to add that extra negative, e to the negative x. Evaluated from 1 to t. Boom. So slick. Now let's substitute in our limits of integration. So this is negative t e to the negative t minus e to the negative t minus negative 1 e to the negative first minus e to the negative first. And then since we're going to be taking a limit, something I always tell my students is put the terms with negative exponents in the denominator. It'll help your brain when you're trying to evaluate the limit. So let me write negative t over e to the t minus 1 over e to the t plus 1 over e plus 1 over e. Okay, you ready? So we're going to take this limit. Let's go right to left, easiest to hardest. These are both constants. If t goes to infinity, e to the t is going to infinity. A constant over infinity goes to 0. But in this case, we have to be careful. Denominator is going to infinity, numerator is going to negative infinity. That's an indeterminate form. Do I know where it's going? Not until I do L'Hopital's rule. So we're going to do a little aside. So let's take the limit as t approaches infinity, negative t over e to the t. So always verify that you have indeterminate form of the type infinity over infinity, or the other scenario where you can use L'Hopital's rule is when you have 0 over 0, only those two cases. Make sure you have that before you proceed, and then you have to tell the people that's what I'm doing. So you have to indicate that you're using L'Hopital's rule. And then now we take the derivative of the numerator and then the derivative of the denominator separately. Okay, usually it'll make things better. So if t gets really big, e to the t is getting really big, we have a constant in the numerator, so this is 0. So now I can say, oh, I know this is also going to 0. So in the end, I'm just left with 1 over e plus 1 over e, which is 2 over e. So what do I care about this limit? If it's a finite number, that tells me the integral converges. So then what do I know about the original series? The sum, k equals 1 to infinity, k e to the negative k, also converges by the integral test. Now, if you've already finished the unit on sequences and series and you've heard about the ratio test, that would be a much easier test, I think, to use. So you can confirm it works beautifully. But again, like I said, we did integral test because that's what the direction said for this problem. So we're just practicing getting really good at that test, okay? But if it's a free-for-all and your teacher's letting you just pick whatever test to use, I would definitely have gone for ratio over this one. I have a few videos on the ratio test, even one with me in a classroom. If you want to watch it, it took forever to record, man. I would really appreciate it if you just at least gave it a thumbs up and a little comment. Okay, let's move on. I do actually have two more for you. This is a nice one. I'm trying to think if there's another test that I would like to use better. No, I think this is the way to go with this guy. Okay. So we have to sum 2 to infinity of 1 over n ln n. It's not an accident we're starting at 2. Because natural log of 1 is 0, so then it would be undefined. So that's why we're starting at 2. To make sure you're consistent too and you don't switch it to a 1. By accident, that would be tragic. Okay, so let's consider a function f of x, which equals 1 over x ln of x. What happened to that n? It looks hideous. Okay. So first I want to check, is f continuous on the interval from 2 to infinity? Well, what's the domain? So natural log, its domain is from 0 to infinity, right? But I also can't include 1 because that would make the denominator 0. So let's see. The domain is going to go, yes, from not including 0 to 1 union 1 to infinity. Well, do we have any problems? We're only looking at 2 to infinity, a piece of this interval, so we're cool. So f is continuous on the subset from 2 to infinity. Whew, that was a close one. Is f of x positive on 2 to infinity? Well, I know for sure x is going to be positive on 2 to infinity. Ln of 2, that's positive, and then it just keeps getting more and more positive, so we're good. Just put a little check mark. And then the last thing I need to check is f decreasing. So I'm going to take the derivative. If you want to remind yourself, it's x ln x to the negative first power. That might help. So f prime of x is going to be negative x ln of x to the negative second, and then we have to do the chain rule, multiply by the derivative of the inside, which is going to be 1 times ln x, product rule time, plus x times 1 over x. So then I'm going to have negative ln of x plus 1, that's all this, right here, and then let me put over x ln of x squared. So look, this is positive. Ln of x plus 1, that's positive. And then I got this big old negative out here. Woohoo! So this one's easy. Less than 0. Done. Cool, huh? Perfect. So we can go ahead and use the integral test. So then now we can consider the improper integral from 2 to infinity of 1 over x ln of x dx. So first things first, rewrite this as a limit before you forget yourself. Then we go 2 to t, 1 over x ln of x dx. How would you evaluate this integral? Yes, just a relaxing u sub. So you're going to let u be ln of x, and then du is 1 over x dx. My new limit's 2. U of 2, that's ln of 2. And then u of t, that's ln of t. So then this is limit, t goes to infinity, ln 2, ln t, and then we just have 1 over u du. Good? Antiderivative's going to be ln, absolute value of u, and then we evaluate that from ln 2 to ln of t. Keep writing lim in the front. If you drop it, the math police will come and snatch you. Write you a citation. Ln of absolute value, ln of t, minus ln absolute value, ln of 2. Okay, we're good. If t goes to infinity, ln of t goes to infinity. So this goes to infinity. ln of 2, I don't know, it's just some number. Who cares? You know what I wrote the other day in class? Everyone freaked out. Instead of writing the word number, I did this. And they were like, why are you writing a hashtag on the board? You guys, back in the day, there were no hashtags. That was the pound sign, which also represented number. Okay, anyways, this limit is infinity. So then what can we say? Well, we can say the integral diverges, right? This improper integral diverges or is divergent. So then I know the sum, n equals 2 to infinity, of 1 over n ln n also diverges by the integral test. Yes, you need to say what test you used. By the integral test. Okay, there we go. How was that? I have one more for you. That's it. Okay. One more for you in this video. There's plenty more in other videos. I have this epic Greek saga. Not really, but you know, it's a 6-hour video broken up into 2 parts where I solve 100 questions on sequences and series. I'll link it in the description. But I do a bunch in there too. So if you need more integral tests, I got you. Again, if you know other tests, you don't need to do integral test for this guy. Direct comparison would work like a dream and be much faster. However, we're doing integral test. Let's consider f of x, which equals 1 over x squared plus x cubed. And let's factor the denominator so we can identify the domain, right? Because we have to establish continuity. So is f continuous on 1 to infinity? What's the domain of f? X can't be 0 or negative 1. So are we okay on 1 to infinity? Yeah, we're cool. Is f positive on 1 to infinity? If I plug in only numbers from 1 to infinity, yeah, we're good. The last thing, I want to check if it's decreasing. So f prime of x, if you want to think to yourself, I think the easiest thing is this is x squared plus x cubed to the negative first, you know? So negative x squared plus x cubed to the negative second times 2x plus 3x squared. So that's negative 2x plus 3x squared over x squared plus x cubed squared. Now this is always positive. On 1 to infinity, that's positive. And then I've got this extra negative. So this is negative on 1 to infinity for sure. Good. Okay, perfect. So now we're going to consider the improper integral from 1 to infinity of 1 over x squared plus x cubed dx. And first things first, you're going to rewrite this as the limit as t approaches infinity, integral 1 to t, 1 over x squared times, let me put 1 plus x dx. Did I write x plus 1 up there? I did, but it's the same thing. I don't know why I flipped it. Excuse me. I hope nobody had a panic attack over that. All right, now in this case, there's no way I can make a u substitution. Before you start stressing, we're just going to find the partial fraction decomposition. Remember when you did that? It's partial fraction time. Partial fraction decomposition. So we've got 1 over x squared. You know, it does look cuter to put x plus 1 instead of 1 plus x. That's probably why I did it. Hope you're okay with that. Now, be careful. X squared is a repeated linear factor. So the decomposition will have the form a over x plus b over x squared. If you're like, oh my God, I forgot partial fractions, it's fine. I have video lectures. I'll help you. Go watch them. They're in the description. You got this. Good? Okay, now multiply everything by the LCD. Don't do too much. It's just x squared times x plus 1. You don't need an extra x, right? Always the LCD. Don't get carried away. Otherwise, it ruins everything. So 1 equals ax times x plus 1 plus b times x plus 1 plus cx squared. I'm not going to multiply everything out. I'm going to first let x equals 0. I picked that because then these terms would be gone. So then 1 equals 0 plus b plus 0. So b is 1. Let x equal negative 1. Then 1 equals, this is 0, this is 0. C times negative 1 squared. So c is 1. And then what do you plug in the third time? Whatever you want. X is positive 1. So 1 equals, I don't know what a is, times 1 plus 1 is 2, plus b is 1 times 1 plus 1 is 2, plus c is 1 times 1. Ooh, look at us, so fancy. So 1 is 2a plus 3, so 2a is negative 2, so a is negative 1. Okay, so we're ready to roll. I know this is going to be negative 1. Sorry, guys, that was like the ugliest arrow I've drawn in my life. B is 1, and C is 1. Cool. Gonna replace the integrand now with these three guys. Here we go. Here we go. You know what? Let's write a narrative. So we have, fab. Limit t goes to infinity. Integral 1 to t. It'll be negative 1 over x plus 1 over x squared plus 1 over x plus 1 dx. Okay, I think we can just integrate already. You guys should be fine. Antiderivative of negative 1 over x, negative ln, absolute value of x. This one here, we can do it in our head. This is x to the negative second, add 1 to the exponent, divide by the new exponent. It'll be negative x to the negative first, which is negative 1 over x, plus ln, absolute value, x plus 1, and evaluate all this loveliness from 1 to t. Okay, here we go. Limit t goes to infinity. Negative ln, absolute value of t, minus 1 over t, plus ln, absolute value t plus 1, minus negative ln, absolute value of 1, minus 1 over 1, plus ln, absolute value 1 plus 1. Woo! Okay. I think, hold on, I'm missing parentheses right here. Okay, let's clean up. Limit t goes to infinity. Now, word to the wise. I've got these two ln's, and when I'm going to take this limit, I already am going to start using my log properties to combine them into a single logarithm. If I don't, you're going to run into a problem. You're going to have an indeterminate form. This term we could see is going to go to negative infinity, and this one's going to positive infinity. Negative infinity plus infinity, that's the same as infinity minus infinity. That's an indeterminate form. So I'm not even going to wait to get there. I'm just already going to combine them because you don't need to do anything beyond use your log properties and you'll be saved. I know, log properties to the rescue. The positive logarithm, its argument goes in the numerator. The negative one, its argument goes in the denominator. So this will be t plus 1 over t. Are we all okay? Oh, good. Okay, minus 1 over t is still there. ln of 1, you're 0. Be gone. Then this is going to be plus 1 minus ln of 2. Plus 1 minus ln of 2. Are we okay? Cool. Now, before you take the limit, because this would go to infinity, this is going to infinity, do a little splitteroo, right? This says t over t, which is 1 plus 1 over t, and then you're home free, really. It'll be so nice. So this is ln, absolute value, 1 plus 1 over t. See that? Minus 1 over t plus 1 minus ln of 2. Okay. So if t goes to infinity, 1 over t will go to 0. So this is going to 1. And then ln of 1, that just will go to 0. Woohoo! And then if t goes to infinity, 1 over t is going to go to 0. So all I'm left with is 1 minus ln of 2. What do I care about that? Just that it's a finite number. So then I know the integral converges. And then from there, what can we say? Ooh, here's another symbol if you haven't seen it. That's therefore. The sum, n equals 1 to infinity, 1 over n squared plus n cubed, also converges, this is too ugly, by the integral test. And that's it. That's all there is to it. I hope you enjoyed the video. Give it a thumbs up. Subscribe if you haven't already. I have so many videos all on sequences and series. They have their own playlist on my YouTube channel. I know it's a tricky topic for many students, but it doesn't need to be. If you have someone who really understands it well and can explain it clearly, it can be one of your favorite topics that you study in your calculus journey. So I hope that I can help make it that for you. And also, don't forget to follow me on Instagram, TikTok, Math with Professor V. I love you guys so much. I'll be back sooner than later. Bye.